Fluminense. He's going to talk about the spectrum of drifted Laplacian, on Rich Solitons, and mean-curvature flow solitons.
It's a great pleasure to speak in another geometric school here. And my talk is about the spectrum of drifted Laplacian on Rich Solitons and mean curvature flow solitons. So this talk contains some results jointly work with Shushen, Chitumeja, Viela, and Dasasco. So first I will write down the notation here to make it easier to follow. All the manifold here are Riemannian manifold. And usually I put a function on the manifold. It's not necessarily infinite. So the Laplacian operator is the most important, one of the most important operators on Riemannian manifold. But I will treat with this operator, which is defined as this one. And the manifold I will work on usually two types. One, to state this, I need to define this notation, which is called Becker-Emery-Ricci curvature. And so the manifold I will deal with is just Rich Soliton, which satisfy rho over 2. Rho is a constant. Or I will deal with the mean curvature flow soliton, which just satisfy lambda x is in Rn in Euclidean space. It's a normal part. Sometimes I will go a little bit further between these two things, because it's convenient to say this one. So when you take some special f in Rn, so it's just the mean curvature soliton in Rn. So this is the basic notation. So I were interested in the spectrum of Laplacian, and we will see what's the relationship with the geometry and the Laplacian on the manifold. So, first, I will leave some notations here. Usually, I will concentrate on non-compact case. That is complete. So first of all, let me record some basic definition of spectrum of an operator. So you have if you take a Banach space, you have a linear operator. So you can define a regular set, which is just this operator is invertible, and the inverse operator is bounded. So the spectrum is just the complement of the regular set. So in a spectrum, there is a kind of spectrum called essential spectrum, which is is not very welcome for the analysis on manifolds. So, but we need to study it. So if the operator has no essential spectrum, then the spectrum is discrete. Discrete means that the spectrum can be ordered. Usually we take as this one, number 2, and it goes to infinite. So, of course, if the spectrum is discrete, the things are much better. So let me record some basic results. So on the round sphere, if you look at the Laplacian operator, it's easy to see. Easy in some sense, it's easy to see the first eigenvalue is 0, and the first non-zero eigenvalue is lambda 1 equals to n times the curvature, the sectional curvature. Yeah. So if the Ricci curvature is constant, so we have the lambda 1 is bigger than this number. So there's a famous result of Nacional or Bata, which says if the Ricci curvature is bigger than or equal to the Ricci curvature of sphere, then the first non-zero eigenvalue is bigger than or equal to the first eigenvalue of the sphere, and it equally holds if and only if the manifold is sphere and the manifold has constant scalar curvature. So if the manifold is non-compact, even in Rn, you have all the spectrum are essential. So and you can determine that the essential spectrum is just the half line. So after several works of Escobar, Shen Lu, Jiaping Wang, and finally we can prove that if the Ricci curvature goes to 0, the limit Ricci goes to 0, the same result holds. A special case says that if the Ricci curvature is non-negative, all the spectrum is essential. So the same result also holds if you look at the Laplacian on the shrinking gradient soliton. That means the rho equal to 1 is shrinking. It goes to 0 is steady and expanding. Actually, it's positive. We can scale it -1. So I will come back for this. So it's convenient. We take a more general notation, which we call the smooth metric measure space with this notation. It's just a Riemann manifold with a function. When you take a derivative, you use the connection or you use the metric. When you want to take integration, you use the new measure, which is like this. You put a weight here. So it is naturally, it comes naturally from the study of singularity analysis for geometric flows, principally for Ricci flow and mean curvature flow. So here, just the notation I have put it here. And a few words about Rich Soliton. There are many interesting things about this. First, it's a generalization of Einstein manifold. And also, for shrinking case, it's more interesting. It is just a critical point of Perelman's functional. So in this case, you can take a first variation, and you can take a second variation. The second variation will give you operator, which likes this one. Like this one, I will start with Q. It depends on the Q. Both of the cases, this is also a critical point of some functional on the smooth metric space. Then it depends on the Q, depend on the case, the Q can change. So if time permits, I will study a little bit this operator, which is related to, actually it's the same thing. Many people are interested. I think we have several talks deal with this operator. It's the number, the dimension of the negative space of this operator is just the Morse index, right? So second variation will give operator like this one. So there are many examples. Because we are a little bit late, I will skip the examples. And anyway, you need to know there are many interesting examples. Among all the examples, there are several ones. There are two examples deserve more attention. One is Gaussian soliton, which like this, you take just take standard metric, you take f is x squared over 4. And another one is cylinder soliton. So in the mean curvature case, the cylinder soliton, generalized cylinder soliton has been proved that they are generic singularities for mean curvature flow. And for Rich Soliton, it's more complicated. We need to deal with this operator, which is much more complicated than mean curvature flow. So even we don't know the cylinder soliton is, if the cylinder soliton is a generic one, but it deserves more attention to these two cases. So here we want to see this question. What about the spectrum for the drifted Laplacian? Many people are interested in this case, but in most of the cases, if you put this a number here of this term, will help a lot. But in our case, usually you need to do something more complicated. I don't have this term. So the space E in the beginning I will choose is this space R2 and H2, R2 and H1. With this measure, namely, we will use this norm in both spaces. So the Laplacian F, the drifted Laplacian, has similar properties with as the Laplacian. So, for example, you have this formula. You just put F here, then you have similar things. You also can define a lambda 1, which is the first non-zero eigenvalue. Usually we call it's not Bott selection. So I have to mention this result is just exclude some case. If you have rich F non-negative, then and F is if F is sublinear, then the spectrum, the essential spectrum is complicated. There are many essential spectrum, and from a result of Monteano and Chapin-1, the estimate this growth is sharp. The growth of F is sharp. So actually, they have for all the static solitons, the spectrum is different from the 0 and infinite. So I'm now recording this result. Just make some normalization to make it easier to see. You have this result. And actually, the Nacional or Butter result is for compact because of the Bonnet-Meyers theorem. So if it's compact, so of course the Laplacian spectrum of Laplacian is discrete. Let's see some examples of drifted Laplacian. In R1, you have eigenvalue. You can find eigenfunctions, which are called Hermitian polynomials, which can be written down explicitly. So in this case, the spectrum is discrete, and you can write down just 0, 1/2, 1, 2, 3, just like this. And for Rn, it's called Ornstein-Uhlenbeck operator. The spectrum is just like this. You have the multiplicities, and you can write down all the eigenfunctions. Anyway, you have this one. The first non-zero eigenvalue of this operator is at least 1/2. So remember that if you, in that case, the f is 1/2, x squared over 4, then in this case, Ricci curvature is 1/2 exactly. The lambda 1 is 1/2 with multiplicity n. And if you look at the cylinder shrinking soliton, so the operator, the lambda 1 is also 1/2. It's quite different from the sphere. When the Nishinovich-Obata theorem says that if lambda 1 is of the manifold is equal to the lambda 1 of sphere, then it has to be sphere. But now at least you have several examples which are not in the case. So there is another history about the estimate of lambda 1. For example, you can estimate of lambda 1 from above and from below. Usually use the curvature bound. You use, sometimes you use diameter. But in this case, there are also similar results for compact case. If the manifold is compact, you have rich F bounded by something, then you can estimate the lambda 1. But you, for example, Andrews, Lely, many people was trying to get a sharp estimate of the lower bound, but in compact case, it's not possible. We will see why it's not possible. So I will just record some facts about gradient Rich Soliton. If you have this equation, immediately you have this equation. And almost immediately you have this equation after some translating of f. So you just take, from these two equations, you just take a difference. You have this one. So you can write this equation by in this form. So from this, you can see this function is almost an eigenfunction, except you need to prove that this function is in R2. If it's not in R2, for example, in hyperbolic space, even for Laplacian, you can find some function. For example, if you look at, you have some function like a minus 1. Well, I will use h equals to 0. You can find some function to satisfy this. But in hyperbolic space, this one is not R2. But in this case, from an estimate, two estimates was done by Detang Zhou and me. We can see the f has this property, and the volume is bounded by the volume of Euclidean ball. So in this case, they are R2. So this confirms that this is an eigenfunction. That means 1 is the eigenvalue. 1 is the eigenvalue. This means for general gradient shrink is Rich Soliton, 1 is a permanent eigenvalue. And this function is a permanent eigenfunction. I call it permanent. It does not depend on the case. So in more general, what happens if you only have this condition, just similar to Nacional Bata, how to say this? First, we need to see that if the spectrum of Laplacian F is discrete or not. It can be confirmed by these two results, actually two results. One is from Bagley-Emery. He said that you have log of F equality. For this condition implies this condition and this condition. This condition means the total weighted volume of M is finite. These two conditions imply that you have log of F equality. And another result is Morgan proved that this condition implies the total weighted volume is finite. So we can prove these two results from this. This application is compact. You have compact embedding, and equivalently, you can see that the spectrum is discrete. So in this case, you don't have essential spectrum. All these spectrum are eigenvalues. So you can have you have this property. I just list here, and the eigenvalue. There is another permanent eigenfunction is 1. The constant function is eigenfunction. The eigenvalue is 0. So we need to understand what happens. So this is the result we obtained for this condition. First, if Ricci is bounded from below by the Ricci F is bounded below by the Gaussian soliton, then the first eigenvalue is bounded below by the first eigenvalue of Gaussian soliton. And the equality holds if and only if these items. First, you have multiplicity, and then, more importantly, you know that it has to be split. So this space is non-compact. That is the reason why the estimate which was obtained by many people in the compact case, the normal bound cannot be sharp, because the only sharp case is non-compact. So in this case, the space has to be something like a cylinder or generalized cylinder. As a corollary, the greater shrink Rich Soliton, which is in this case, it splits if and only if the lambda 1 is 1/2. An interesting phenomenon is that there are another group of people which worked on the measure theory. They have many results about this kind of stuff. Recently, what we found that there are recent papers, he mentioned that he used a totally different method to prove that some generalized rigidity result for the measures only in Rn, not on remaining manifold. It's done by Filippi and Figali. I will skip the proof. I'll just say a few words about the proof. The proof mainly used the Bohr formula, weighted Bohr formula, and we need to justify some integrability of the functions. There is a basic problem here. For compact manifold, you always have equals to 0. The question is that if it's not compact, in which case it holds. So this happens here, and it will happen in some other places. So usually you don't know the integral of this one is 0 or not. That's the problem. You need to justify. But in this case, you can prove that the integral of this one is 0. So you can follow this proof, and then you get the desired result. On the other hand, I want to report some results for the self-shrinkers. A self-shrinker is just a hypersurface which satisfies this equation, just like this one I written here. And it's a special solution for mean curvature flow. And also you can consider the sigma as a critical point of V, which is just called a weighted area. You just take this area. So it's a critical point of this functional. Also, you can consider it as a minimum hypersurface if you change the metric. So here are some examples. Again, this as I mentioned before. We can consider this as a cylinder, and this can be considered cylinder when k is 0. And here are some examples in the curve in R2. And in R3, you have this one. Also, there are embedded torus, immersed sphere. And the immersed sphere, if it's embedded, Brenda recently proved that the round spheres are only embedded ones with genus 0. And the Cody-Minikos proved that the generalized cylinders are only generic singularities. Generic means that if in some stability, if it's not generic, you can perturb the singularity such that the flow goes away. So it can be removed by perturbation. The cylinder ones cannot be removed by this kind of operation. So here are some notations. I just want to. So the sigma-Lefferman form is defined like this, like this. If you take this case, take this f, we will use this the same notation. This is a traditional notation, but I just want to use this one. You can compute Rich f because you have f here. You can restrict on sigma. Then you get a smooth metric measure space. And in this case, you can compute Rich f. Rich f is 1/2 minus a squared. So you can see here, a squared is always non-negative. So that means Rich f is less than or equal to 1/2. It's just opposite to the Rich f bigger than or equal to. So what about the spectrum of this one? The result that we proved before cannot be applied here because Rich f is less than or equal. You don't know Rich f is non. Even maybe he can change the sign. You don't know it's non-negative or not. But if you only consider the proper ones, which is natural, in the mean curvature flow case, you can find some additional information for the measure on this space. For example, we care about the total measure. We care about the volume growth of the self-shrinker. So, of course, this is topological information condition we prefer to use. Finally, we can prove that for self-shrinkers, these three conditions are equivalent. So that makes many theorems more cleaner. Yeah, we don't need to assume the many conditions. So that means proper immersion, finite weighted volume, and the volume groups, polynomial volume groups are equivalent. So from this, we can prove, we have to go back with the log subleft equality. We can prove that the spectrum of this drift Laplacian is actually discrete. So again, a good news is that this is discrete, and in this case, we always know that the first eigenvalue is less than or equal to 1/2. It's injured. Also, we can have a better log subleft equality. Unfortunately, we don't know what's the rigidity result in this case at this moment. But later I will talk about the result. We can estimate lambda 1 from below. Yeah, just correspond to the result of. So now before proceeding, I will talk about some permanent eigenvalues and eigenfunctions. For example, we have 1/2. We have 1 eigenvalues, and also we have constant function, coordinate function restricted on the manifold, and this function restricted on the manifold are eigenfunctions. Or we also can do some computations which are quite interesting. If you take this function, you can estimate the integral of scalar curvature. Very quickly, you can use this result to prove some geometrical properties for self-shrinkers. For example, we can prove that any self-shrinker properly immersed in Rn plus 1, intercept all the members of this set. This set is just, I will give a picture here. So this set are all the spheres with center on somewhere and with some radius, just like this. There are some 2 special cases. When P is 0, it's just the round sphere, this one. And when T is infinite, it's just a half space. So that means our self-shrinker must intercept with all the members here. For example, if you take this member, that it implies the half space theorem. So that means self-shrinker cannot be contained in the half space here. Also, you can, if you take this sphere, you can see that the self-shrinker cannot be contained in this sphere. Also, it cannot be contained outside this one. And the direction P can be any vector. So that means you have a big family of spheres which must intercept all the self-shrinkers. It's quite interesting. So I need to mention that the half spheres first proved by Marcus and Espinal. Also, you can consider the cylinder case. I think I don't have much time here. I will skip this proof. If we generalize this case, we can also define a self-shrinker in Rich Soliton. So if F is convex, we also can prove that the Laplacian F is discrete. Here is the proof. I just want to mention, we just to make some transformation to this one. Laplace F equals to this one. So you only need to consider this operator to see if the spectrum is discrete. And here we don't have log sub left. We have some equivalence of proper immersion with the volume, but if we use this one, we also can prove that the spectrum is discrete. This method of proof you just need to prove that this potential function here is proper. This function, you have this function here is proper. So this proof can be applied to prove some other result. For example, you can prove that or self-expander, you have spectrum discrete. Or in other words, if lambda is negative, it's also you have so for self-expanders you also have a discrete spectrum. Also, you can give another proof for shrink-rich solid. Notice that if you can prove that the spectrum is discrete, you can go back to prove the compact embedding of between the spaces. So in this case, you can give another proof for the compact embedding of between the subleft spaces. So this is the result I want to mention here. I will go quickly. So actually, we can also generalize the Choi-Wang's result to the F minimum, the self-shrinker case, bigger than or equal to this one. When k equals to half, it's 1/4. Oh, okay, I have 14. I thought I have 5. So I want to say a few words about the stability operator. So the stability operator is just like this one. For the self-shrinkers, Q is just a squared plus half. We can prove that if, I forgot the norm. If the norm of the second manifold form is not too big, I mean, it can be infinite, but if the growth rate is not so big, then the operator has discrete spectrum. So it's a good thing that it can imply, for example, you can prove that it have finite index, because in the case of discrete spectrum means that the eigenvalue goes to infinite. So if you take 0 somewhere, the number of negative eigenvalues is finite. So that implies the self-shrinkers, if the second manifold form is like this, you have finite index. Also, maybe you can apply to some traditional techniques to prove to estimate the finite index. Another application, if you look at the first eigenvalue now means the bottom spectrum, the limit, the lower bound of spectrum. As we know, for compact case, the first eigenvalue have multiplicity 1. So if you have a discrete spectrum, or maybe you don't need the discrete spectrum, you have some properties that if you look at the lower bound, the bottom spectrum, bottom eigenvalue, then you can prove that in a non-compact case. In some case, it also has multiplicity 1. So it has some quick applications. I will mention 2. The first one is that you look at the self-shrinker, you have A, the second manifold form, which is a 2 tensor. It's an eigentensor for this operator. Notice that this operator can be simply generalized to tensors. So you have eigentensor with eigenvalue 1. So if you take a trace, you have eigenfunction with eigenvalue 1, which RF applies on the functions. You still can work with this equation. You have a lower bound, have a this inequality here. So this means that means if h does not change sign, you can prove that this operator is this operator minus, if you put on the same side, has some, that means you have first eigenvalue here. So you can prove that these two are proportional. That means this inequality is equality. So the equality holds if and only if it's a round cylinder. So you can prove that in this case, if h does not change sign, then it's a round cylinder. So that is exactly the proof of Cauchy-Minico's proof, but in this case, you can simplify it much. So if you look at the bottom spectrum, you can determine some things. So another application, we can generalize this fact to any Schrödinger operator. It does not matter what Q is. What you need is two things. You have two functions. One satisfies this one. Another function satisfies this one. One is positive. Then if you have, you don't need to be assume one of the, for example, this one implies you have eigenfunction, but you don't need to assume the eigenfunction is R2. Actually, you only need to assume that the eigenfunction does not grow very quickly. It's a technical condition, but you can see some examples. For example, the Kr is the kappa is t squared. If it's t squared, then it's 1 over t. It's non-increasing, and then it's divergence. So in this case, they are proportional. So it's a generalization, but it has the application interesting. So if you look at translated soliton, exactly if you compute the translated soliton, if you compute the growth rate of a square on green plane, green hyperplane, which I think it has been mentioned in the course of in the mini course. So exactly this property. So you need to generalize this technique to this case. Then you have this theorem. So sigma is a translated soliton. We can only do it in two-dimensional case, 2 and 3 dimension. So if the green hyperplane, if and only if h does not change sign, and the growth rate cannot be controlled by r squared, quadratic growth. So in this case, you have a uniqueness for green hyperplane in no dimensions. I think that's all I want to talk about. Thank you.